Alright, how's it going, people? The purpose of this video today is to cover essentially a reaction to Wikipedia, as well as some code that GCC will generate. So where I'm going to start our conversation, Wikipedia. So if you've watched the previous videos, there's this thing called a calling convention, which dictates roughly how we should use registers and how we will interact with the stack. Is there a better resource? I don't know. Wikipedia works out just fine. So let's scroll down here, and you'll see a lot of different calling conventions described. Obviously, we are working with ARM. Wikipedia refers to this as A64. Generally, I've heard of it referred to as ARMv8. I think that's a more common term. And what you'll see here is, according to this calling convention, we have some expectations for how you use the registers. Up until this point, you've been using registers 0 all the way up until 15 without really considering whether you can or not. And it turns out that registers can only be used under certain contexts. There are generally two types of registers. There are user visible registers. In this context, user is a terminology from operating systems referring to the program that you were attempting to code and run yourself. The other registers are special and reserved registers that generally you should not be modifying. Sometimes you will not be able to access them at all, and sometimes you will, and you just need to know not to mess with them. Or if you do, you need to preserve the value of those registers on the stack. So let's take a look at some of these registers. So I'm going to start with the bottom, and we'll go from the top. Alright, so remember that ARM registers, A64, the word size for the register is actually 64 bits, which is why you see all of these referring to X, okay, not W. W is like the half addressing mode. So registers 0 through 7 are intended for argument values passed to and from a subroutine. So you've kind of seen that actually. So with main, you know that basically if you want to return 0, you have to put 0 into W0 to basically return a 32-bit value for 0. You've seen examples with malloc and printf that were using x0 to place an argument. So what happens is, when you perform a branch and link, in order to pass arguments to a function, you have to place the arguments in a register beforehand. This is a little different than how it works in C. In C, when you do the function call, like there's the parentheses and you put the arguments in the parentheses, there is no such thing at the assembly level. So basically, the calling convention defines how you pass arguments from one function to another. The caller will place arguments in a left to right order in these registers, and then the subroutine, or the callee, when control is given to the callee, will assume that the registers were placed in that specific order. What is known or assumed is the function prototype, and you go from left to right, storing the arguments there. I also want to point out that these are the same registers for the input and the output, so that means when a function returns, it should use x0. So generally speaking, you're always only ever going to have one register to pass values in and out of. All right. We also have an indirect return value address. So that would be if you had some sort of object. So for example, if the function prototype that you're creating, its return value was some sort of pointer to an object, such as a class, struct, string, array, etc., you would actually return it in x8 instead of x0. All right. And then x9 through x15 are local variables caller-saved. Caller-saved means that when the caller calls a function, if it's caller-saved, if the caller expects the value to be the same on the return from the subroutine, that it should have saved the values. All right. What that means for you in terms of implementing functionalities are that x9 and x15 are roughly your scratch registers. All right. We were using x0 through x7. That was perfectly fine. Actually, it turns out that x0 through x7, they're not they're caller saved. They're not callee saved. So technically speaking, you can use registers x0 all the way up to x15 as just scratch and not have to worry about saving the registers or preserving their value. All right, moving up here, a few of these x17 through x18, that actually gets into the registers that are special and should not be used unless you know what you're doing. So I want to note here that it says caller-saved. So for example, if you intended to use x18 or register 18, you would have to save the value of x18 onto the stack, do whatever you wanted to do, and then before your return, revert the value of x18. All right, or just don't use it, basically. x19 through x28 are callee-saved. So in terms of user-facing registers, you kind of also categorize them into like into caller-saved scratch registers, which are like you don't have to preserve the value, or callee-saved. If you use a callee-saved register, you have to revert its original value before the return. All right. We'll go over a couple examples on that, like in later videos. Generally speaking, it's kind of advanced. It's kind of weird, actually, and it's honestly not something that even GCC would do. It's a little bit of an advanced like assembly technique. All right. The only reason you'd use those is if you somehow ran out of registers. I mean, you got up to 15. Hopefully, you don't end up needing those additional registers, but if you do, just make sure to save them, basically. We also have x29, that's the frame pointer. Something that I haven't mentioned yet is there's actually two separate stack pointers. So the stack pointer is a global pointer that indicates the bottom of the stack, all right, and we're moving that to allocate a frame. By the calling convention with this particular instruction set architecture, there is also a frame pointer that is placed at the bottom of the stack as well. And that might be a little weird, like why do we need a double pointer pointing in the same spot? Well, the purpose of this is actually for certain algorithms that require a stack, so there's a difference between the stack that we're talking about that is holding our local variables and our return address, etc., and the concept of a stack abstract data type. If for some reason a functionality or subroutine that you need to implement called for a stack or queue, you would actually use the frame pointer as a movable pointer within your stack frame to implement that stack ADT that you needed. It's a stack within your stack, basically. Honestly, that's again really advanced, and I don't imagine we're going to cover any examples that end up using it, but it is something to notice when you'll see the GCC example today. You'll notice that it uses both the stack pointer and the frame pointer. And basically it'll the frame pointer is a callee-saved register. So that means that generally, if you're going to use the frame pointer, you'll need to save the original value of the frame pointer onto the stack and then revert it before jumping back to the caller. All right. Now x30 we're pretty familiar with. All right, but it's still a discussion we need to have. You have 32 general purpose registers. Whatever you do, don't use x30 as a scratch register. It's the return address register, And then finally, our last register, right? x31. Remember, we're zero indexing here. When you start counting at 0, it's like n minus 1. So there are 32 registers, but it only goes up to 31 because we started counting at 1. In the examples I've given previously, I literally write it as SP, but technically speaking, it is register 31. So it is definitely an important register. It is user visible, but you don't want to be using that as a scratch register. All right. So where do we go from here? Let's take a look at an example function call to see the interaction with how GCC prepares arguments being passed to a function and how it returns them. All right. So we're working with some simple C code here. We have a main function that calls functionality we've created called myAdd. It passes the value 1, 2, 3, and 4 to this function. Looking at the top of the code here, you can see the prototype should return an integer, and it accepts an integer A, B, C, and D, and it will return the concept of adding A, B, and C, and D together. Let's go ahead and use GCC to compile this thing into some assembly code to see what happens in terms of the calling convention. So the command we're going to use is GCC, display all warnings. When you're generating assembly code from C code, remember you need a big S flag for only wanting assembly. We're going to compile it into main.s, and the file that I want compiled is main.c. Remember the extension for assembly code is .s. Alright, so I execute this, no errors here. Let's take a look at main.s. So one of the things that I want to reiterate here is that whenever you use GCC to make assembly code, there's going to be a lot thrown at you. You have to be able to identify the specific parts that are important, and to try to ignore parts that might seem weird that we haven't really discussed yet. All right, I'm going to skip. So clearly this is the definition for my add, and I'm just going to skip this thing, and we're going to go to the main. Basically, let's take a look at the main. All right, so the first instruction here is something that's super weird. It's something that we haven't really seen before in the main. I want to point out here, main itself is a function that's called by the supervisor process. So technically speaking, it is a function, and it needs to preserve certain registers. If you remember from the earlier part in the video, x29 is our frame pointer, our pointer within a pointer, and x30 is the link pointer. Both of those are callee-saved. This instruction, by the way, let me just convert this thing to some code that we've seen. When we were implementing code on the stack, we would do the following. We would move the stack pointer, and then if we wanted to store anything to the stack, we would then add them to the stack with individual instructions. SP8. So just an explanation of these instructions here. I am decrementing the stack by 16 bytes exactly. I am saving the return address to the bottom of the stack frame, and then this right here, we haven't really messed with the offset yet, but putting an 8 there means you take the base pointer and you add an offset. Why 8? Well, the X registers are 8 bytes long, so you want to make sure that the frame pointer, or I'm sorry, the return address is stored at the bottom of the stack, and that is 0, 1, 2, 3, 4, 5, 6, 7. Basically, those bytes are associated with that return address. That means the next free space on the stack will start at the top there, or 8, SP plus 8. 8, 9, 10, 11, 12, 13, 14, 15, basically would be the next free space. So you're saying here to save x29, which is your frame pointer, just above the return address, and that boundary is important so they don't end up colliding with each other, basically. All right. Now, these three instructions happen so often, generally at the start of every function call will you do this sort of thing, that an optimization that the designers of ARM made was to create a single instruction that stored 2 registers directly onto the stack at a particular address, and also to move the stack pointer. And that's a hardware level instruction. That's what this is. Basically, if you're wondering why I was avoiding using GCC to compile some of the examples, this is it. Basically, we had to wait until we had learned about the stack to even understand what GCC would even do out of the gate in terms of instantiating a function. So what this does is it will store, STP literally means store a pair of registers at the bottom of a stack frame. You allocate 16 bytes for that purpose. The bang actually means to move the stack pointer down by 16 bytes before attempting to store the pair of registers one above the other in memory. Okay, moving on here, ignore this whole CFI, etc., stuff. These are like linker directives, and we don't need to pay attention to that. So actually, before we even get into the rest of this, I want to point out this instruction. We now learned about the frame pointer, which is like, you got the stack pointer and you got the frame pointer, which points to the bottom of your stack frame. This instruction, move stack pointer to x29. This doesn't move the stack pointer. It sets the value of the stack pointer, and it sets the value of the stack pointer in x29. So basically, the previous function call had its own frame pointer. So basically, if you're moving the stack pointer value into the frame pointer, you're causing the frame pointer to move to the bottom of your own stack frame. And that's what that instruction does. But then, all this is basically the calling convention. The main function itself, our main function is so simple it doesn't even use a stack ADT, but like I said, the calling convention is just something you do. You got to do it, basically. Anyways, moving on here. This right here, these 4 or 5 instructions are our call to my add of 1, 2, 3, and 4. All right. From this perspective, main is the caller. It is the function that is calling my add. Remember, the template for this is 4 integers, and we wanted to pass the value of 1, 2, 3, and 4. And I guess GCC did it in reverse. It appears like it is right to left, but I want to point out here that the indexing actually goes from bottom to top here. So the first argument we pass is a value of 1, and that is passed through register W0. So that means that when the callee receives control, it will assume that the registers were passed in order, where the first argument was in W0, the second argument was in W1, and so on. And that's why we refer to it as left to right, because the indexing, if you're going up from 0, this would be the first, second, third, and fourth argument placed in the first, second, third, and fourth registers that are defined specifically for the purpose of passing arguments. And if you remember from earlier in the video, that's register 0 through register 7. So you can see here that GCC is basically doing that. It is passing in a left to right order the values 1, 2, 3, and 4. Then it's performing a branch and link. All right. Just to close our discussion on main, what do you see here? I'm going to go ahead and delete these just so that we can focus on these 3 instructions. Like I said, that CFI procedure, whatever, that's linker stuff. We don't need to pay attention to it. So on a return, main will return 0. We're familiar with the idea of these return registers. Register 0 is the return register, so that means the operating system, when it receives control from main, will look inside register 0 to see what the return argument should be. This LDP is the inverse of pushing the stack frame. This thing pops the stack frame. All right, it loads a pair of values x29 and x30 from the stack. It does it in order. It's basically the match for this instruction. So you can imagine this instruction basically saving x29 and x30 to the stack and allocating 16 bytes. This instruction restores x29 and x30 and reverts the stack pointer back to where it was, noting that it does that because these values for how many bytes you want to use for your stack are equivalent. Okay, and then it returns. All right, in return, obviously that returns from your subroutine. So that is that from main. Let's take a look at our function for my add. All right. Now, before we do that, I think we ought to just recap what our expectations are for our function. So just a quick recap here before we wander off into the assembly again. Again, my add is a integer returning function, and it is given 4 integers, A, B, C, and D, and it is adding all 4 of those together, and the concept of those 4 values added together should be passed through whatever the return register is. All right, let's get back into the assembly now. All right, so we're back in the assembly now, and now we're looking at the myAdd function. I'm looking at the code right now. Oh, come on, GCC. It's not even consistent with the calling convention stuff, but whatever. You'll see some weird stuff happening like that. So it appears like it is moving the stack pointer by 16 bytes. All right, it's going to be a little important. I'll explain what it does there. Basically, let me just add a couple of items here to sort stuff out. So the function myAdd receives control, and what is the first thing it does? It takes the value of W0 and it copies it to the stack. All right, so this is an important concept. This is called shadow copy. All right. At the assembly level, a shadow copy is the concept when the callee receives control. It will take all of the input arguments that you've passed it, take the values of those arguments, and store them into local variables. Where it stores the local variables to is the stack. So I guess if you think about it, how much stack space do you need, basically? Well, we're passing it 4 arguments. All of them are integers. Integers are 4 bytes. 4 times 4 is 16, which explains why we have a 16-byte offset on our stack pointer. So basically, we move the stack pointer down by 16 bytes, and that is enough space for us to store what appear to be input arguments 1, 2, 3, and 4. So SP, we'll start at the bottom here. So basically, at the bottom of our stack frame, we have SP. At SP, we store W3, so that would be the input argument D. Bytes 0, 1, 2, and 3 store D. Just above that, at SP plus 4, 4, 5, 6, 7 is W2. And if you remember for how we pass the arguments, W2 is C. So it, from there, basically it looks like it's storing it in reverse order on the stack, local copies of A, B, C, and D. All right. Moving on here, so we see GCC now in implementing the arithmetic expression A plus B plus C plus D. Okay, this is actually one of the points where I'm going to be a little critical of GCC. When it evaluates this expression, it actually dereferences A, B, C, and D as if it doesn't have local copies already in registers. Now, if you're an assembly developer, you would have known to refer only to W0, W1, 2, and 3, but GCC is a little dumb, and it will dereference that from its local versions. So basically, SP plus 12, looking at our previous code, incoming to the function, that was the value of A, actually. This one, SP plus 8, that was the value of B. So it is attempting to add A and B, but it is sort of restoring local copies of what it believes to be A and B from its stack. All right, a little wasteful, because technically W0 and W1 were holding those values anyways. All right, what does it do? So it adds them together. So basically, this instruction will add A and B together and store the result in the temporary register W1. All right, this also illustrates the point with input argument registers not being callee-saved. Notice that it is actually clobbering those values. It does not need to restore the values of any registers with in the range of 0 to 7. You can use them freely as scratch. Okay. All right. What are these other instructions? Well, SP plus 4, looking over here, that was W2. So that's C. So basically, what this is doing now is it is dereferencing C, and we now have an expression where W1 is equal to A plus B plus C, right? Because it's placing the value of C into W0. It's adding A plus B to C, so therefore W1 is now equal to A plus B plus C. And then, you could probably guess that down here, same thing happens. It dereferences D, because if you remember, when we set up the stack frame, we placed D at the bottom there, basically at the stack pointer. It's placing it into W0. So that means that this thing will be A plus B plus C plus D. All right? And it places the result into W0, which is convenient because W0 is the register where you return a value through. All right, so we don't need any other instructions to move any temporary values into W0. We basically leave it as is. We will pop the stack and then return. All right, so that's our first exposure to function calls. GCC provided this example to us. Now, as an assembly developer, what is your reaction to this? It sucks. Okay. I don't know why it's doing this, basically. we already have the values like 0 through 3. So technically speaking, I'm just going to delete all this. All right. It's no good. It's not great. Why is it dereferencing the values? You know, basically the values are already in W0, 1, 2, and 3. Basically, what you can do is add W0, W1, W0. All right. So what does this do? Actually, let me reorder these. So adds A and B and places it into W0. Let's just keep doing that, basically, where we will accumulate W2 into W0, and we'll accumulate W3 into W0. Actually, so that's that, basically. That would be adding all 3 of the input arguments together. I'm going to leave this, though, because if you remember, at the C level, there's this concept where, like, the input arguments are copied into local versions of themselves, local instances of the variable, and that's actually what shadow copy does. So according to our calling convention, that's just what we want to do there, basically. So let's go ahead and compile this thing and just verify that me messing around with it achieves the desired result of adding 1, 2, 3, and 4 together. Let's say set a breakpoint here. So we call the function myAdd, and I'm going to create a breakpoint done just before the return 0. We'll set a breakpoint there, run the function, and see what we can do there. All right. So to compile this thing, we'll call GCC. We'll display all warnings. I want the output to be main.out, and I'm going to pass it our main.s assembly file. All right. So I'm going to call main.out just to make sure it runs, no errors. Let's check out GDB. We'll run it with GDB and set a breakpoint to done, basically. So remember, done is the endpoint of the code. What we're going to want to look for is that the return argument register should have added the register values 1, 2, 3, and 4. All right, so that would be 10. So let's go ahead and run this thing. All right, no errors. Let's go ahead and display the value of the registers. I'm going to want to check out register X0, and there you have it. After I updated GCC's code, we were able to get a value of 10. All right. So as far as where we go from here, we can now implement proper functions for some of the algorithms that we had gone over in previous videos. That's it for today, everybody. Have a great day.